This summer, I worked under Laurent and Yann in the GeePs laboratory, modeling an apparatus for the magnetic inspection of pipeline integrity. Pipelines are the most favorable way of transporting large quantities of liquids and gases. Proper maintenance and threats can cause environmental hazards, property damage, and threaten life. Non-destructive testing is a technique used to determine the pipeline's integrity by measuring changes in magnetic flux and is a reliable and safe way to determine pipe abnormalities. Stress not only affects the performance of pipes, but determines lifetime and has a great effect on the magnetic permeability of ferromagnetic materials. Take iron, for example. Iron has 4 unpaired electrons in a 3D orbital. These unpaired electrons are called magnetization electrons and are caused by electron spin. The atoms align themselves into domains, which act as magnetic dipoles. Since the domain walls are randomly oriented, there is no net magnetization. When a magnetic field is introduced, the domains align in the direction of the magnetic field. When the magnetic field is removed, the domains remain aligned and continue to exhibit magnetic properties. This behavior is known as ferromagnetism. This summer, I created a 2D and 3D model in COMSOL multiphysics that could detect stress in steel pipe by looking at changes in Earth's terrestrial magnetic field. Stress is known to change the magnetic permeability of ferromagnetic materials. To model stress, the defect's relative permeability ranged from 100 to 1000, while the non-defective pipe was given a relative permeability of 1000. The goal was to determine whether a 10-degree defect and its angular position were measurable by a nanotesla sensor. The pipe was located 1 meter below the soil. The induced terrestrial magnetic field was 50 microtesla, oriented at an angle of 45 degrees. A one-dimensional sensor was placed 1 meter away from the pipe to collect data on magnetic flux density using a finite element method. It was confirmed that change in magnetic flux density is dependent on the defect's relative permeability and position. Afterwards, a new defect was introduced. This new defect contained a missing angular sector that penetrated 50% of the pipe's radius, or 3.5 millimeters. A new study was conducted, this time to observe how size and location of the defect affected the terrestrial magnetic field.